Interaction between mathematics and physics, number 2. So welcome everybody, both live and on Zoom. And it's my pleasure to introduce Viviane Baladi as a first speaker from today. She will be talking about Sinai billiards from a mathematician's point of view. So thank you.
Thank you very much. So I'm very glad to give this talk today. I was trying to think this morning if I ever gave a talk in such a beautiful room. And the only thing I could remember which compared in some way to this was a talk I gave in Italy also, in Corinaldo. It's a small city on a hilltop in Tuscany, and it was in the theater, which was also very beautiful, but in a different style. So I'm going to talk about Sinai billiards today. And it's rigorous results. So that's why I put mathematician's point of view. And also because the story involves introducing some new techniques to solve the problem. And I will hide the gory details from you, and I will try to explain why these new techniques help to answer some problems on which we had been stuck for over 20 years. So since I'm Swiss, I have a plan. I'm not sure I will be able to follow it, but I have a plan. First, I will tell you what a Sinai billiard is, either in discrete or continuous time, so maps or flows. Then I will remind you some classical results. So of course it starts with Sinai, and then a few other results up to the late 90s. And then I would like to tell you about some results which have been obtained in the past 10 years. So the first new result actually is a new proof of an old result, and that's where the new technique appears, which I would like to briefly explain. And this new technique opened the door to proving several results which I, as a mathematician, find exciting about the flow map and about the flow billiard and the map billiard. So I hope I will have the time to explain these results. And then, if there are a few minutes or seconds left, I will explain what open problems remain. Okay, but what is a Sinai billiard? So it's a very simple, embarrassingly simple mechanical model. So I will talk about periodic billiards. So the billiard table is actually a torus, so it's in dimension 2. If you don't like the torus, you just think about a periodic billiard in the two-dimensional plane. And there are finitely many scatterers. So on all the pictures, the scatterers are perfect disks, but that's not needed for the results. What is important is that there are closed domains which are disjoint, and that have a boundary which is smooth enough, C2 plus epsilon or C3, which is with strictly positive curvature. So Sinai billiard in this talk is a synonym of dispersive billiard. I don't need the perfect disks. And there are two pictures on this slide, two examples. One of them, the scatterers all have the same radii, and the only parameter is the distance between them. And the other is another simple example. We have two scatterers with different radii. Okay, so that's the problem. And what's the dynamics? Sorry, that's the billiard table. And now what is the dynamics that we consider? So there is a continuous time dynamics, so the flow, and a discrete time dynamics, the map. The flow is what you imagine. So when you are on the torus and you are not meeting an obstacle, you just go straight ahead with unit speed. And when you hit one of the scatterers, there is a specular reflection. That's a flow, which is also called a periodic Lorentz gas. And sometimes, either for physical reasons or just because mathematically it's easier, you look at the map instead. So you discretize, and you look at the map between collisions. So the billiard flow is a map on the table times minus pi pi. Pi is an angle. And the billiard map lives on a smaller space, since you can only, you leave from the boundary of a repeller and you look at next time you hit the boundary. And there are coordinates, natural coordinates, which are used, which will not maybe appear in many formulas today. But just to give you an idea, the first coordinate is the arc length along this boundary, and the second is an angle, which by convention is measured to be the post-collision angle with a normal when you are talking about the map. So you can think of a union of cylinders in these parameters, but you don't have to think so. I'm not going to give many formulas. Okay, so that's a very simple system. And now there are bad news and good news. So the bad news are what makes the system interesting, hard to study, so interesting to study. So I start with the bad news. The bad news is that this map has singularities, okay? If you identify the incoming and the outgoing angle, the flow is continuous, but the map is not continuous. Whenever you have a tangential collision, so when you graze one of these scatterers, then if you move your angle a little bit on one side or a little bit on the other side, you will have completely different behaviors. Either you will hit the scatterer or you will miss it, and this creates discontinuities in the map. So the map is only piecewise 1/2 Holder. It is bijective, right? The system is invertible, but that's not the problem. The problems are the singularities. So those are, Calandro, you have a complaint? No. So, so let's introduce some notation to handle these difficulties. The set of tangential collisions is called S0. So that's when the angle is plus or minus pi/2, because the angle is measured as a normal to the tangent. And as we're doing dynamics, it's not enough to look at this set, which looks pretty harmless, right? It's just a union of curves, but we have to iterate it. And when you iterate this finite union of curves, you have to do it infinitely many times. Then you get a dense set of curves, okay? So the singularities, they are really all over the place. It's a dense set of curves. That was the bad news. Now the good news. The good news is that the system enjoys hyperbolicity. Actually, it enjoys uniform hyperbolicity. So you have some directions which are uniformly contracted and some directions which are uniformly expanded. And one way to view this is to see that there are invariant cones for the derivative. So of course, the derivative is not defined everywhere, right? You have to avoid these singularities, but whenever you are not at a singular point, you will have strictly invariant cones. So how do you define these cones? So remember, a big K is a curvature, the curvature of the obstacle. So since we have an assumption that the boundary is C3, and we have this strict convexity assumption, the curvature is bounded from below by kappa min, which is K min, which is strictly positive. And since the curve is C3, it's also bounded from above, so K max. So by using this K min and K max, we can define these cones of directions. And the other parameter which appears is tau min. So tau is a free flight time between obstacles. And since the repellers are close and pairwise disjoint, this time is bounded from below. So tau min is strictly positive. So we define two cones of directions. And then there's a claim that you can check, which is that not only the derivative maps what I call CU, so the unstable cone strictly into itself, and the inverse of the derivative of the inverse maps the stable cone strictly into itself, but it does so with a uniform hyperbolic constant, which actually can be computed. Well, this is a rough lower bound, but a rough lower bound for the hyperbolicity is 1 + 2 times tau min K min, which is strictly bigger than 1. So we have expansion bigger than lambda in this unstable cone and contraction stronger than 1 over lambda in the stable form. So that's the information we have about the system. And another thing which I forgot to say, but which is probably very clear for this audience, is that this is a Hamiltonian system, and so the Liouville measure is preserved. So we don't need, a problem in dynamics very often is that you need to work very hard to get the physical invariant measure, but here it's just given for granted. Liouville measure is invariant for the flow. For the map, you have to work just a little bit harder, and you have to find which is the normalization function. But it's not very difficult to see that the measure which has a density cos phi, remember was this angle with a normal. The measure with density cos phi is invariant under the map and is absolutely continuous with respect to Lebesgue, of course, by definition. So the story starts with Sinai, more than 50 years ago, who showed that these are the only absolutely continuous invariant probability measures for the flow, respectively, the map. And in addition, they are ergodic. In fact, not only they are ergodic, which means that the time averages converge to space averages, but they are mixing. Okay? So we have mixing property. And this is mixing in a qualitative sense. And a little bit later, well, actually, very little time after that, Galavotti and Ornstein showed a stronger mixing property, which is a Bernoulli property. But this is still qualitative. Okay, so for the moment, we only know that we have qualitative mixing. And it took almost 30 years before quantitative result could be obtained for the billiard map. Okay, I already mentioned it's easier to study the billiard map than the billiard flow. And the first result about qualitative mixing was for the billiard map. It was by Lysan Young, 98. And Chernoff, I didn't talk about the finite horizon assumption yet. I will in the next slide, but Chernoff lifted the finite horizon assumption just a year afterwards. And what did these people show? They showed that we have exponential mixing. Okay, so the precise statement is in the last line. So if you take two Hölder observables, so the test functions need to have some modulus of continuity. If you take just L2 observables, you don't get any rate of mixing. But if you take a Hölder modulus of continuity, you fix the Hölder modulus of continuity, then you will get some rate of mixing, which is exponential. So you get a factor psi, which is strictly smaller than 1. And you will get this decay of this correlation function, which is psi to the k. What I have to the left is a correlation function for the observables psi1 and psi2 at time k for the discrete time billiard, so the map T. So that was a big success in dynamical systems. And now I want to move on to more recent result. And from now on, I need to make a stronger assumption, which was satisfied in the two pictures which you saw, which basically is that there are no trajectories which do not meet any repeller. And more precisely, we even want to exclude the possibility of having a trajectory which just grazes one or several obstacles along its way. So now we assume that there's finite horizon, and this implies that the tau max, the maximum free flight time, is finite. Okay, and now let's try to think about the billiard flow, okay, which maybe is more natural from the physical point of view. And we add this assumption, and with this assumption, until a couple of years ago, the best known result was faster than any polynomial, and a little bit later, a slight improvement, stretch exponentials, like e to the minus square root of the time, okay? Just to mention that this finite horizon assumption is not just because we are too stupid to handle the infinite horizon. For infinite horizon billiard flows, then the correlations decay very slowly, like 1 over the time. Okay. So all the results I mentioned up to now, so the proof of Lincei about the exponential mixing for the map, or these results which I just mentioned about stretch exponential and super polynomial for the flow, they use some kind of symbolic dynamics. Okay. Symbolic dynamics mean that you have some Markov, you define some kind of Markov partition, which actually cannot be finite, it has to be countable. And using this decomposition of the space, you define some symbolic system, which is called a Lincei tower, or I mean, there are other names. And then you reduce some kind of subshift on countable many symbols. And then you get the results I mentioned. And 10 years ago, a new technique was introduced for this problem, which is to use, instead of symbolic dynamics, just define an operator acting on functions or distributions which live on this manifold. Remember, we have this simple two-dimensional for the map, three-dimensional for the flow compact manifold with boundaries. That's where the system is acting. So instead of constructing an artificial symbolic system, we just work on the manifold. And what is a operator, the relevant operator? It's just a composition by the map, and you divide by the Jacobian. So why the Jacobian? Because you're interested in measures which have, at least for the moment, measures which are related to Lebesgue. And so if you use this normalization dividing by the Jacobian, then the dual of the operator will preserve Lebesgue measure. It's just a change of variable formula in an integral. So the new ingredient in this new proof of the result of Lincei was to define a good space on which the operator should act. So it turns out that there is absolutely no way to define a space of functions on the manifold such that this operator will have a spectral gap. And this is because the dynamics has expanding directions, but also contracting directions. So the inverse dynamics has contracting and expanding. And when you compose with contraction, that's not good for, it doesn't improve regularity, quite on the contrary. So you need to find a good space of distributions. And a good space of distributions will be anisotropic because there will be some stable and unstable directions play a very different role. And just to mention that this was not the first time ever that anisotropic were used in dynamics. I think the first time is a paper by Blankeller-Liverani almost 20 years ago. And they were used by many other people and for several problems. But to study systems with singularities, which, let me remind you, is the main obstacle to study billiards. To study systems with singularities, there was a key step, a paper of Demos and Liverani in 2008. And it's on that work that Demos and Zhang built. And how did they implement their proof? They used this paper of 2008, but they needed to fight an additional difficulty. So this other paper was about piecewise hyperbolic system. But in that previous work, the derivative was supposed to be continuous all the way to the boundary. So whereas for billiards, we have these singularities, and the singularities correspond to discontinuities in the map, but I didn't mention it. The derivative also blows up when you go to the boundary. I mean, certain boundaries, not all of them, certain boundaries. So this creates problems when you have unbounded derivatives. You don't have what are called distortion estimates. If the second derivative is not bounded, you cannot control distortion. So the trick to avoid this difficulty is to partition the space in countably many pieces close to the boundaries using homogeneity layers. But let me repeat, this is not something that you use to define a symbolic dynamics. It's something that you use to define the norm. Okay, so to define the norm, you will use these homogeneity layers. And then there's another problem due to the singularities that you have this generates a lot of complexity when you iterate. And so you have to you have to show that the hyperbolicity is strong enough to counterbalance the complexity. And this is what people call growth lemmas. So these are the technical parts. And what they do show then is that you have a nice spectral picture for the operator on the Banach space. And maybe I should show the picture, yes. So you have this, what is called quasi-compactness. So the main step is to show that the essential spectral radius is strictly smaller than the spectral radius, because this operator is bounded, but it's not compact. So the first thing you have to do is to show that the essential part of the spectrum is far away from the spectral radius. So they did that, and they also showed that you have the Perron-Frobenius picture, meaning that the maximal eigenvalue, which is 1, remember that you are to the operator fixed Lebesgue measure, so we expect to have 1 in the spectrum. So the maximal eigenvalue, which is 1, is the only eigenvalue of modulus 1. So we have the spectral gap, and then we have maybe some eigenvalues of modulus strictly smaller than 1, but outside of the essential spectrum. If they exist, they are called Ruel resonances. And I think you can all imagine that once you have a spectral gap, you get the exponential decay of correlations by spectral decomposition. And if you have other eigenvalues, if you have other Ruel resonances, then you can write a more precise asymptotic expansion for the correlation. And they did many other things, Demas and Zhang, but maybe I will skip that because otherwise I will run out of time. Maybe I just mentioned that very recently, actually only last year, some examples of billiards were constructed where you can actually prove that there are other eigenvalues besides the eigenvalue 1. The eigenvalue 1 we know is there. The other Ruel resonances, until last year, we didn't know if it was possible to find examples where they existed. Now we know. Okay, and now I move to, I told you now what is a new tool. This is new anisotropic space. And now what can you do with it? I mean, because giving a new proof of an old theorem is maybe not so exciting, even if you're a mathematician. So what is a first new result? The first new result was to show exponential mixing for the billiard flow. So this is much more difficult than the map. Why? Because when you have a flow, the flow direction is not expanded, it's not contracted, so you have a neutral direction, and this creates a lot of difficulties. But by using anisotropic spaces, we were able to show exponential mixing. So if you look at the statement, it's exactly the same statement than for discrete time. If you fix a Hölder exponent, then you get some decay rate, strictly smaller than 1, which holds for all test functions which have this Hölder exponent alpha, with a prefactor which could depend on the observations. So it's a little bit like the spectral picture I showed you a moment ago, except that now you have discrete time. So instead of having just one operator, you have a semi-group of operators. And so how do you study the spectrum of a semi-group? Well, you look at the generator and you study the spectrum of the generator. So instead of having a bounded operator and the spectrum is going to be inside of the disk, we're going to have half planes. And so the first thing you need to show is that there is the spectrum is going to be in the half plane real part of z smaller or equal to 0, right? The 1 becomes 0 when you go to generators. So we have an eigenvalue 0 for the generator, which corresponds to the fixed point for the semigroup. And you have to show that there is a half plane to the left, which contains all the essential spectrum. So there is a strip in which the spectrum of the generator has only eigenvalues of finite multiplicity, which are isolated. That's, in some sense, the easy part, which is very similar to what you do for discrete time dynamics. But then there is a hard part, very hard part, actually. But fortunately, the key idea was given to us by Dima Dolgopiat almost 25 years ago now. And it consists, well, once you say it, it seems obvious, but believe me, it was not obvious 30 years ago. You have, when you look at the expressions for these semigroups, you will get something which looks like an oscillatory integral with a free flight time appearing in the exponential multiplied by some imaginary number. So you get oscillatory integrals, and you have to show that that they behave well, and this allows you to avoid the difficulty which you can have for continuous time, which we did not have for discrete time, which is that since now we are talking about a line and a half plane, if you have countably many eigenvalues, they could accumulate on this vertical line. We have to show that this is not possible, and this is what the Dolgopiat estimate tells us. And to implement this Dolgopiat estimate, basically we need to use the fact that the return time is very far from being a constant. And this, at the geometric level, follows from the fact that since the flow is Hamiltonian, there is an invariant contact form, and this gives us a kind of control we need. Okay, so that was the first result we got by exploiting this new technique. And now I would like to go to a second class of new results. And what I will do is I forget the flow, right? Let's go back to the map. As I said, it's easier to study the map, so let's go back to the map. But let's ask harder questions about the map. And the harder questions we're going to ask is, instead of just studying the Lebesgue measure or the Wheel measure or this absolutely continuous invariant measure with a cosine, which I put on one of the first slides, let's try to find other natural invariant probability measures. And there is one natural invariant probability measure, which people in dynamics or ergodic theory like to study. And this is a measure of maximum entropy. So MME is the abbreviation for measure of maximum entropy. What's the definition of measure of maximum entropy? When you have a discrete time dynamical system, which preserves a probability measure, this defines, associates to the pair number, which is a Kolmogorov entropy. And you would like to know if this Kolmogorov entropy has a maximum. So if the soup is realized, you would like to know if it's realized, and if it's realized, how many, if there is a unique measure of maximum entropy, or how many there are. And of course, once you have a measure of maximum entropy, you would like to know if it's mixing, and ask all the usual questions that people in dynamics like to ask. So the first reaction that people have is they say, no, but the dynamics is hyperbolic, it's expansive, so it should be trivial, right? The problem is that people are used to thinking of continuous dynamics, and the billiard is only continuous if you remove this countable union of curves, which is dense, and the manifold without this countable union of curves is of course not compact, right? So you can, either you have a continuous map on a subset which is not compact, or you have a discontinuous map on a compact set. In any case, it doesn't fit in the usual framework, which allow you to tell, oh, the Kolmogorov entropy is upper semi-continuous, so you have a maximum. So you cannot do that. So you have to do something else. And well, we did it, but it was harder than we thought, than what we expected. And in particular, we needed to introduce an assumption. So we did it in two steps. First, we found a natural candidate for the maximum of the Kolmogorov entropy, which is called the topological entropy. And how do we construct this candidate? Well, it's like a measure of the complexity, right, of the topological complexity. So for each n, we have the nth iterated singularity set, which is this finite set of curves. It cuts up the space into connected components. So you just count the number of maximum connected components, and you see how this grows. You take the log and you divide by n, and you take the loop. This gives you a number. Okay, and then now I tell you the second step is to define this sparse recurrence to singularities. Of course, in reality, it didn't happen like this. In reality, we tried to construct the measure. We couldn't, and then we introduced this assumption. But okay, let me tell you what the assumption is. So the enemy are the singularities. So you want to say that you have a billiard table where you cannot spend too much time hitting singularities. How do you quantify this? Well, you fix some angle which is very close to the dangerous angle of pi over 2. You fix some length n0, and you fix some proportion, some fraction S0, strictly smaller than 1. And you say that the billiard table enjoys sparse recurrence to singularities, meaning it doesn't hit singularities too often, if all orbits which have this fixed length n0 have at most a proportion S0 of collisions which are bigger than phi 0 in absolute value, meaning which are very close to being grazing. And sparse recurrence to singularities means that you have found n0 and S0 satisfying condition A. So of course, you can take n0 very big and phi 0 very close to pi over 2, such that in addition, if you multiply S0 by log 2, you are strictly smaller than this topological complexity, which I defined just above. So what the hell is this log 2? Maybe you remember that I told you that the map is piecewise 1/2 Hölder. The 1/2 comes from the fact that, well, just think of the perfect circle. If you look at the perfect circle and you compute the dynamics, you will see that there are square roots which will appear, and the log 2 is, the 2 is coming from the square root. So it's really there. Okay, now just a few remarks about this assumption. Of course, we are shocked that we needed to make an assumption. So first remark, since we assume finite horizon, S0 can always be taken strictly smaller than 1. If you assume that there are no triple tangencies, then you can take S0 strictly smaller than 2/3. Then you can try to check on examples. And the good news is that all the examples we checked satisfy this condition. We don't know any examples which don't satisfy this condition. We suppose that this condition is generically true for all billiard tables. I mean, it's true for almost all billiard tables, but we don't know how to prove. Okay, now I told you the assumption. What is a theorem? The theorem is that once you make this assumption, you have a measure of maximal entropy. Not only you have a measure of maximal entropy, but it's unique. Its Kolmogorov entropy is exactly this topological number which I introduced. And this measure is rather well behaved. It doesn't have atoms. It has full support, charges all open sets. It's mixing, so it's ergodic. In fact, it's even more than mixing, it's Bernoulli. And it is T-adapted, which is something you need if you want to talk about Lyapunov exponents, meaning that if you look at the logarithm of the distance between a point and its and the singularity set, when you average with respect to this measure, you get a finite number. Now, maybe you didn't notice it, but I didn't claim, let's keep this for the moment, I didn't claim anything about the speed of mixing. I just said that the measure is mixing, right? I don't know about the speed. And there's some additional things which maybe I will skip, or maybe I just mention it. We know that this measure maximum entropy, because you could ask, I think this question was asked, I don't remember if it was Bunimovich or Chernoff, but one of the famous Russians, asked if the measure of maximum entropy, which at the time was not known to exist, coincided with the absolutely continuous invariant measure. And what we prove is that it coincides with the absolutely continuous invariant measure only if all the periodic orbits have the same Lyapunov exponents, which of course seems highly unlikely. I don't think this ever happens, but we don't know how to prove. Maybe with so many physicists in the room, maybe we can find somebody who can actually give some, at least some idea of how to prove that, but we don't know how to prove that such billiards don't exist. Okay, and there are bonuses, but maybe I skip that. And I'll tell you a few words about the proof. And as I tell you a little bit about the proof, maybe it will become clear why I did not claim exponential mixing. Well, maybe I should, sorry, spoiler alert. I mean, it's just because there is no spectral gap, right? We cannot prove that there is a spectral gap. But let's try to understand why this problem is more difficult than the previous one. I don't know if you remember, but the operator for the absolutely continuous measure, we had composition by the map and division by the Jacobian. For the flow, the Jacobian is constant equal to 1. For the map, it's a little bit messy, but it's fine. Here we do something. We have to change the weight in the transfer operator if you want to get an operator whose maximum eigenvector will give us the measure of maximum entropy. And what we have to do is to change the weight and replace by this full Jacobian in the denominator by the stable Jacobian. The stable Jacobian is going to be basically always smaller than 1. But when you go close to the boundaries, it will actually go to 0. It's going to be basically equal to the cosine of the angle, right? So we are dividing by 0, and this is always problematic. And because of that, we were not able to work using the homogeneity layers to control the distortions. There was no way to do that. So if you cannot control the distortion, you have to work the norm in the Banach space will have to be weaker. You cannot use a Hölder modulus of continuity. You have to use a logarithmic modulus of continuity. And because of that, we lose the spectral gap, okay? However, we still get the control on the spectral radius. We can still get some, we still have some weak compactness control. We can construct this maximal eigenvector, and then we can construct this measure maximum entropy with the output. So that's the result. And once you have the measure of maximum entropy, and you have the SRB measure, the measure which is absolutely continuous with respect to Lebesgue, it's natural to consider the one parameter family of measures which interpolates between these two. And the parameter is this t here. So if I put t equals 0 in this formula, I'm just maximizing the Kolmogorov entropy, right? So I'm looking at the measure of maximal entropy. If I put t equals 1 here, by something called Ruel inequality, or maybe the Piecewise, I don't remember. I mean, a classical formula in dynamics, you are going to get the measure which is absolutely continuous with respect to Lebesgue. So what we do now is we interpolate between these two. And remember that for t equals 1, we had very nice picture, spectral gap, everything. For t equals 0, we have a much worse situation. We didn't have the spectral gap. Anyways, so let's define this pressure, and let's define an equilibrium state for this potential minus t times the logarithm of the unstable Jacobian to be any t invariant probability measure realizing this supremum. So let me just remind you, we're still talking about the map now. I won't say anything more about it. So, oops, sorry. Yes. So yeah, this basically I already said, and now it's written. It's not the real. It's a Piecewise entropy format. Okay, and so that's the last result which I will mention today. I think I still have 10 minutes, right? So this is the last result I will mention today. And what we could do is we found a limiting value, which we call T star, which is strictly bigger than 1. And between 0 and this limiting value, we have a very nice picture, meaning that we know that there's a unique measure which realizes this maximum, and this is called equilibrium state in ergodic theory, classically. And not only we have a unique measure which realizes maximum, but this measure is mixing, it has full support, doesn't have atoms, it satisfies this adapted property which we had for the measure of maximum entropy. And cherry on the cake, we have the quantitative mixing properties. So we have exponential decay of correlations for further observables. And these statements are for T strictly between 0 and T star. You could wonder what happens when T goes to 0. And remember, when T is equal to 0, which we could only construct the measure of maximal entropy if we satisfied an additional condition. And the result is that if this additional condition of sparse recurrence to singularities holds, then what you would expect holds, meaning that when the parameter T goes to 0, the equilibrium states for T converges to the measure of maximal entropy. So I will say a few words about the proof, maybe not too much because everybody's getting tired, the temperature is slowly rising. And then I would like to say, to mention a couple of corollaries. It's basically like for the measure of maximum entropy, except that we won't have the problem that we have there. We won't have this terrible function in the denominator. But the starting point is the same. We first define a topological candidate for the pressure. And we show that it has all the nice properties that you would expect for pressure if you have done any thermodynamic formulae. So it's convex, strictly decreasing. And also, it's related to the actual pressure we want to study, meaning at least we have the lower bound. Okay, there is a bug in my slide. I don't know exactly where this comes from, but let's ignore it. And then we show the spectral claim. So we have to look at the transfer operator with a different weight. So the parameter T appears here, right? If you take T equals 0, then you get this horrible Jacobian here. If you take T equals 1, then you get no horrible Jacobian. And if you take T in between, you get the horrible Jacobian with a power strictly smaller than 1. And this actually is enough to allow us to implement the homogeneity layers, etc., etc. Except that the closer you go to 0, the more difficulties you have to implement this approach. And the spectral gap actually that we get, maybe actually this is on the next slide, the control that we have on the spectral gap becomes weaker and weaker the closer you get to 0. Yes, it's here. So that's what I try to say too quickly in 2 sentences. So it's explained a little bit here. So we go back to the homogeneity layer construction. So we try to control the distortion because we can. So we have this anisotropic space, which allows us to control the distortion. However, if the parameter is very close to 0, or actually it's very close to this T star, we have to change some of the parameters which appear in this norm. So these norms are quite ugly. I mean, you get used to, it's an acquired taste. I mean, you get used to them and then you tend to love them like your ugly children, but I don't want to shock you, so I won't show. There are a lot of parameters and you have to tune the parameters when you go very close to 0, very close to T star, and then you lose this control of the spectral gap. Of course, I'm not claiming that this is the only possible norm, and maybe some more clever person can do better, but we cannot keep the spectral gap when t goes to 0, t goes to t star. Yeah, okay, so just to say that it's more complicated. And now to finish, let me just show you some additional information, which comes out of the spectral picture, the spectral gap. Well, this pressure has all the features that you could dream about, meaning that it's analytic, and it has expected formulas for the first and second derivatives. I guess if you're brave enough, you could compute more derivatives. In particular, the second derivative looks like a Green-Kubo or correlation, whatever, the usual expression. And you can see that the second derivative vanishes if and only if the stable Jacobian satisfies some very rigid equation, which we expect is never possible, but we don't know how to prove. And I gave this talk in Geneva last month, and several people in the audience, I don't remember if this was Giuliani or Bodino, were curious about what is a meaning of these measures mu t when we change the parameter. And I don't really have a good answer to this, but maybe I have just a little remark, is that because of this theorem, we know that the Lyapunov, if you take the measure mu t, you fix parameter t, then the second line of this theorem tells us that the Lyapunov exponent of mu t almost every point is equal to this average of the unstable Jacobian with respect to, the Lyapunov exponent is the average of the unstable Jacobian. By the first the first equality in the theorem, this is p prime of t. By convexity, by strict convexity of the pressure, if you have two parameters, which are one is strictly smaller than the other, if S is strictly smaller than T, then mu S almost every point sees more average expansion than a full measure set of mu T points. However, both measures have full support, so yeah. So I mean, maybe we should still work and try to understand what is the physical meaning of these measures, but it's natural to study them. And the last point is that, again, if you have two equilibrium states for different parameters which coincide, we expect this never happens, but we don't know how to prove that. What we can prove is that if it would happen, then we would have some very strong consequences that the stable Jacobian is basically constant. So I think that's all I want to say. I have a central limit theorem, but maybe say it. Ah, yeah, future work. So there are lots of open questions. One of the open questions is to construct the measure of maximal entropy for the flow. So I have a PhD student who's, I mean, I think it's a question of weeks now, or maybe days. Maybe I shouldn't have put this on the slide. So measure maximum entropy for the flow, I think very soon we can claim existence and uniqueness. A problem which is harder to solve is to control the speed of mixing. So we don't have the spectral gap for the measure of maximum entropy, so we don't have the exponential mixing. We kind of expect that we should have some polynomial mixing. This comes from some estimates which I didn't show you on the slides, but we don't know how to do this. And then there are many other open problems. I mean, finding real resonances for the flow. I told you we have examples of real resonance for the map, but we don't know any single example of billiard flow where we can say actually, besides 0, there are some other eigenvalues of the generator. We want to show that this condition of sparse recurrence to singularities is generic. We would like to control the number of periodic points, and maybe I can end with that. Why am I interested in periodic orbits, periodic points? If you know something about periodic orbits, you can construct dynamical zeta functions, dynamical zeta, or dynamical determinants, and then we would like we would have a different way of describing the spectrum of these real transport. So I think that's it. So in any case, my doesn't work anymore. So thank you very much.
Thank you very much for your nice talk. And let me open if we have for questions for the speaker. Either here or...
Is there any attempt to define a non-commutative billiard or quantum billiard?
I think there are some people working on, I don't know actually. I don't, do you know, Carangelo? I don't think so, but.
In quantum chaos, they essentially study the Laplacian on
but
billiard. That is quantum billiard in some sense. But
yes, but I mean, yes, so that's true. But I mean, I'm not so, yeah, that's true. But for me, it's more a model. Okay, correct me if I'm wrong, but the people who are doing that, it's more that they would like to say something about the actual billiard and they replace it by a model. No?
well, no, there is this chaotic
quantum unique
quantum chaos.
Right, no, that's true,
yeah.
that's true. That's
So
true.
they
Yeah,
look
yeah,
at
that's
the
true.
eigenfunction
That's
at
true.
high energy, and they want to see if they are
yeah.
equidistributed. So this is a huge business.
Yeah, yeah, no, you're right, you're right. Yeah, I had forgotten this, yes.
Sorry, yeah. So you were talking about the open problem about periodic points and the Ruel zeta function.
Yes.
But I don't know. It seems that if you don't have some kind of spectral gap, or you cannot prove that the essential spectrum is smaller than the true spectrum, then it's not really clear to me what hope there is to do something.
So yes, so let me say better. So for the measure of maximum entropy, meaning if you just want to count the periodic orbits, we have the lower bound. I mean, what we get, the information that we get is enough using some result of Sarig and, you know, all these people who like, yeah, because what I didn't say is once the measure is adapted, then you can live to some symbolic dynamics of Lima Mateus, which I don't like, but which we can use. And then we have some lower bound for the fixed point. If you just want to get this, oops, no. But if you just want to get the upper bound, yes, here. If you just want to get the upper bound, I don't think you would need the spectral gap. Now you're right, if you want to get some more precise information like a zeta function and something like that, then you need a spectral gap. So I'm not claiming that there is any kind of strategy to understand the zeta function when there is no spectral gap. So this is much less ambitious. I just want to go back to the SRB measure, I mean to the Lebesgue measure or absolute continuous measure, and where we have the spectral gap, and then understand the dynamical determinant. And for the moment, with Roberto Castorini, we decided to, you know, do our homework, because for the moment, even for piecewise expanding maps, except in dimension 1, or in higher dimension, if you have a piecewise affine map, it's not known. So we went back to piecewise expanding maps in any dimension, and we are trying to understand the dynamical zeta function for piecewise expanding maps. Because if we cannot do that, it seems a little bit crazy to look at the billiards, yes.
So I wonder how much is known about, sorry, I'm here. How much is known, I mean, if any of these results can be transferred to three-dimensional Sinai billiards?
It's very hard. So for example, if you just look at the billiard map, not even the flow, and you ask the question of the speed of mixing, then the only result which exists, as far as I know, is a conditional result, which says that if you have some control on the complexity, which maybe is a little bit similar to our sparse recurrence conditions. Actually, I don't think formally the conditions are equivalent, but they have a condition that the complexity is not too big. Then they can show exponential mixing. But they do this by using the Ly-Sang-Young tower. And so to transport this result to the three-dimensional billiard flow would be very, also the Dolgopiat estimate is much more complicated in higher dimension. So Yeah, maybe what I should say is that controlling this complexity is much more difficult. So already for the two-dimensional billiard, this is a problem, and high-dimensional, yeah, it's obviously a natural question, but for the moment, there are very few results.
If we have some more questions. If not, I think I have one. Are there like technological applications of Sinai billiards, like problems like of building some hardware that can be like helped with your analysis or this analysis, as far as you know?
I don't know. Maybe one remark which I should make is that what I was discussing today, it was only periodic billiards. So that's maybe a too strict assumption, right? You would like to have some more freedom. If you think of the plane, you would like to have more freedom and, you know, allow different things. I know that Calangelo has recent results for this kind of situation with Mark Demers, but I don't know if there are any concrete applications. Are you going to patent your result? And so.
Okay.
Bunimovic.
I don't know if it counts for technology, but there is an old paper of Bunimovic in which he used billiard in order to study water, internal water in the ocean, and how, you know, depending from salinity, there are blobs in which there is some reflection of the internal water in the ocean that I don't know if it is how far it went, but I don't know if it is a real technology application or it's just that it was stuck on an oceanographic boat due to the system there for several years. So it was just had to do something. It was doing billiard anyhow, no matter what. I don't know.
But maybe just a remark that if there are some applications, it would probably be important to know the quantitative information, right? So to have qualitative mixing is probably not enough if you want to have applications. So that's one of the reasons why we really want to know if you have exponential mixing and to have some control on the exponential rate, etc.
Okay.
Thank you.
Okay. We have another question.
What is the real motivation for billiard? In the sense, it's an interesting model, or do they have some universality? So certain a class of dynamical systems with such properties, such and such, are billiard, so to say.
So I work in France, but I did my PhD in Geneva with Jean-Pierre Ekman as an advisor with mathematical physics. So my tastes are more to the, you know, interesting model side. Although in France, people working dynamics in France, they more like to have this, you know, big theories and so on. So I don't think it fits in a big theory about classifying dynamics, and to be honest, if it does, I don't really care. And so for me, it's more an interesting and difficult model. And I think the gas, you know, it was Boltzmann, it was gas. I mean, studying gases, the initial motivation. So although myself, I'm not really checking, you know, if it applies to any physical model. For me, the motivation, for my personal motivation, is more, this is a very interesting problem, very difficult, and it comes from physics. So let's look at it.
Okay, so let me check if there are questions from home. Doesn't seem to be the case, so thank you once more for your very nice talk. And now we have coffee break. We resume at 11:30 in half an hour.